Hello, everyone. I've just returned to the classroom. That turned out I had made a mistake in how I find dispersion relation. So I'm going to clean that mess up now. I apologize for that. So I want to emphasize everything in the notes is correct. I just transcribed something from those notes and that proofing is all later. So the dispersion relation is when you assume u of xt is equal to e to the minus I omega t e to the I kx. I forgot the minus in here. So as a result of that, that's why I got all of the dispersion relations being the negative of what they are in the notes. Turns out though that the growth factors that I wrote down are also correct. So what I'm going to do is I don't care if this is considered overkill, I will rework all the examples that I carried out so that you have the correct thing. Okay, so we have, so the idea is you substitute into the PDE, and this is for linear PDEs with constant coefficients. Doesn't work so well when it doesn't have those properties. At least it's not as informative. Okay. Because for a linear PDE of constant coefficients, when you're assuming periodic boundary conditions, a general solution would be a linear combination of terms of this form, where k is related to the integers, or might be the integers, depending on the domain. If you substitute this into the PDE and then solve for omega as a function of k, that tells you what omega needs to be for this form of u of xt to be a solution of the PDE. Then you know that your PDE, at least for the initial value problem, is a sum of terms of this form where you have a right omega. So this gives us information about how the waves in the solutions Fourier series behave. Do they grow or decay in amplitude? Do they shift to the left, shift to the right? Do they travel with the same speed or frequency dependent speeds? Which would be dispersion. So this is valuable information we can get about the qualitative behavior of a solution. Now, in addition to the dispersion relation that relates omega to k, I see on the notes that they actually have not omega but w, but we'll just go with omega. And you also get the growth factor, and that is e to the minus, it's just the time-dependent part, e to the I omega t. So you substitute this into the PDE, solve for omega, and then you compute the time-dependent part of u of xt to get an idea as to how the waves behave over time. Often you might only be interested in the absolute value of this, but the growth factor is defined to be e to the minus I omega t. All right, so now I will rework the examples. So we have the, I won't do every single one as in most of the PDEs that are new to today's discussion. UTP equals CUXX. So what you do is you substitute this into the PDE, and when you take a derivative with respect to x or t, is this going to be this again multiplied by some constant? If you differentiate this with respect to t once, then it's multiplied by minus I omega. If you differentiate with respect to x, it's multiplied by quantity ik. So in this case, if I substitute this in, then the second derivative with respect to t, I get minus I omega quantity squared e to the minus I omega t e to the I kx is equal to quantity I k squared e to the minus I omega t e to the I kx. So on both sides, you get e to the minus I omega t, e to the I kx times something. That's always going to happen for such PDEs. So for later examples, I won't write this part, just the factors are multiplied by, and you can figure out what those are. So these cancel. And now I have, so minus I omega quantity squared is omega squared. Okay, actually it's going to be minus omega squared. And that is equal to minus k squared. So omega squared I apologize. I guess I'm just not with it today. This should be c squared. And over here, I should have also c squared. So minus omega squared on the left equals minus c squared k squared on the right. So I have omega squared equals c squared k squared. So omega is equal to plus or minus ck. So this is the dispersion relation for the wave equation. Then I take that omega and compute the growth factor. E to the minus, and then I have plus or minus, e to the minus I plus or minus ck t. Now, what we have is, regardless of choosing plus or minus, we have e to the I times some positive or negative real number, emphasis, real number. So, if I take the absolute value of this, then it is equal to 1. That's called a conservative, when the waves don't change amplitude at all. And because, when omega is equal to a linear function of k, that's when you have advection. Whatever's multiplying k, a constant, indicates the speed of propagation, and plus or minus indicating the direction. So because we have both plus and minus, we have propagation to both the left and right. If you recall D'Alembert solution to the wave equation in one dimension, you have like f of x plus ct and f of x minus ct, indicating propagation of the initial data f of x to both the left and the right. Okay. All right. Now, the minus sign here, so negative constant corresponds to the propagation to the left, with plus sign to the right. Okay. So that's the first example. Second example, convection diffusion. Okay. So I'm going to just write down what e to the minus omega t e to the I kx gets multiplied by when you take the appropriate derivative. Convection diffusion equation is ut is equal to cux plus duxx. Cux is a convection term, duxx is the diffusion term. So substitute in, and what you get on the left side is minus I omega, just that, after canceling the exponentials. And on the right side, you're going to get ICK, and then you're going to have minus dk squared. So then if you divide by minus I, which is actually the same as multiplying by I, because I times minus I is 1. So you get omega, which I want to isolate, is equal to minus ck minus I b k squared. So that is the dispersion relation in this case. When you get the growth factor, you take e to the minus I omega t. So you get e to the minus I, actually it's e to the I c e and e to the minus d k squared t. Now, this first part is absolute value 1, but this part, e to the minus d k squared t, that is exponentially decaying. So the growth factor goes to 0. Okay. One last example is Schrodinger equation, which is of interest in quantum physics. It's a rather unusual equation, which is I ut, so I squared minus 1, the imaginary unit, equals uxx. So when I take a derivative with respect to t, you're going to have I times minus I omega, but that's going to give me omega on the left side. And then on the right side, I'm going to have the quantity ik squared. That's going to be minus k squared. So that's the dispersion relation in this case. So unlike the previous two, we don't have a linear term. So but we don't have any advection going on. The growth factor is e to the minus I omega t. That simplifies to e to the I k squared t. The absolute value of that is 1, but we have frequency dependent propagation of each wave. So that indicates dispersion. All right, so here we have the correct dispersion relations derived, matching what's in the notes. So sorry about the misstep back here, but messed up everything else. If you have any questions about this, please let me know, whether it's in the next class or in between. Thank you.